account managers for more information or to get links to all that stuff too. All right, so we're going to have 4 speakers today kind of spread across the Texas and Louisiana. So in alphabetical order, David Newt, automation specialist with the Runs Company in Houston. Luis Ramos is actually not a solution architect title anymore. I'll let him explain that perhaps when he comes up to speak. With Rockwell Automation out of Houston. Brandon Singh is a network specialist with the Runs Company up in Dallas, Fort Worth. And myself, I'm in New Orleans and an automation specialist. So our topic is resilient networking protocols. And we're going to kind of focus on DLR, but we also have some other things on tap today. So just a quick highlight is we're going to look at device level ring. We will look at Parallel Redundancy Protocol, or PRP, redundant infrastructure. There's some new releases there. And then we'll look at some other resiliency protocols, as well as some DLR reference architectures at the end. So with that, I'm going to turn it over to Brandon. If Brandon, you want to take control, I'll let you drive the ship for a moment.
Good morning. Can everybody hear me?
Yep.
Yes, sir.
All right. So I will be handling the DLR portion of today's webinar. High availability networks help prevent the loss of production caused by media breaks in infrastructure and failures. Media breaks and infrastructure failures can be intermittent, so it's not always something you're going to see in a former life. From enterprise IT, we call those ghosts in the network, where it blips every once in a while. I'm not sure where it came from, what happened. Those would be your intermittent issues. Can be difficult to physically locate because you don't know where it came from. And then they can also be difficult to repair. And what it means is that it takes a long time to observe. You may see it once, and then it may not come back again for a couple hours. It may not come back again for a week, but you'll see that same issue occur again. And it'll be troublesome, and it'll cause a lot of headaches. Network resiliency topics to be covered that we're going to talk about today. Redundant media, device level ring, PRP, Parallel Redundancy Protocol provides both media redundancy and a degree of infrastructure redundancy. We'll talk about some redundant hardware and infrastructure, the 1715 redundant adapters, 1756 redundant adapters, rep, and flex links. So with redundant media and infrastructure, so this here are your basic topology designs. Starting from the left going to the right, you have your redundant star, you have your ring, and you have your linear topologies. Now, from the cost perspective, from the left-hand side, it is the most expensive. Going toward the right, it gets a little cheaper. But as you'll see on the graph on the bottom, the more expensive end tends to have less issues with the intermittent issues, and then you have a more redundant system. And as you move toward to the right, it does get a little cheaper. It is a little easier to implement, but your redundancy and your resiliency on your network does go down as a correlation. Now with device level topology, as far as applications, you have your linear topology, which is very comfortable level, traditional field-based technology. It helps minimize the cost, as I was saying. It was on the right end of that graph. It's a very simple network and very simple network cabling. It's applicable for certain applications that physically have linear layouts. If you have a very narrow facility, for conveyor applications. If you're running conveyor belts, again, those are very linear, straight lines, a lot easier to handle. Also with material handling applications. And then you have your ring topology. It makes the linear topology into a ring and provides a singular fault tolerance. The network is still functions very linear, and it has a single break point. It's a better fault tolerant over normal star topologies. Its resilient protocol is needed in order to keep packets from circulating the ring forever. It can be reconfigured to a linear topology in event of a fault, which is a good thing. And it detects ring restoration and reconfigures back to running into a ring from the linear topology. Network convergence. Network convergence is basically the time it takes to heal when a fault is detected. It's a measure of how long it takes to detect a fault, find an alternate path, and then start moving forward network traffic across the alternate path. The MAC table must be relearned, and multicast and uplinks must be relearned also. That all takes place within the switch itself that's connected to that particular network. During the network convergence time, some portion of the traffic is dropped by the network because the internet connectivity is lost and doesn't exist. If the convergence time is longer than the logic controller connected timeout, the IACS devices on the affected portion of the network may be stopped operating due to the effect of the industrial application. Essentially, you have your controller on the network. It has a timeout feature, but if the network and the switch can't detect a fault and fix it in time, it'll time out, and your controller will time out and shut down. Not a good thing to let happen. With device level ring topologies, DLR is a level 2 protocol, so you would need a level 2 managed switch to help with that. It's also transparent on higher level protocols. Single ring topology, fast fault detection, and ring recovery. There is a ring supervisor that helps manage the entire thing. And within that ring, you can have a secondary supervisor in case the fault is on the supervisor. The secondary will take over. But you do generally have a dedicated supervisor on the network. It is an ODVA open standard, enabling suppliers to develop compatible products. Support for the ring and linear topologies can be done via fiber or copper. Network traffic is managed through time delivery, QoS for quality of service, and precision time protocol. The ring is, as I said earlier, it's a single fault tolerant network. And it's designed for 1 to 3 millisecond convergence times, which can be pretty quick. Some other examples we'll see later on today are faster, but this is for 1 to 3 milliseconds. And to the right, you'll see you have a linear topology, and then below that you'll have the topology of a ring setup. So in this instance here, we have a ring topology. Now you do have a supervisor which blocks traffic on one port, and then it sends out a beacon or just kind of a self-check on either direction to detect if there's a break anywhere in the ring. And if it does detect one, it'll route the traffic the other way. Once the ring is restored, the supervisor will hear with the beacon still continuing to check out, the supervisor will realize that the ring is restored, and then they'll transition back to a normal ring setup and again block off that port that's normally blocked in a normal functioning ring. As faults are detected at a physical layer, all faults are detected at the physical layer. Physical layer failure detected by protocol-aware nodes. Status message is sent by the ring node and received by the supervisor. So depending on where the fault is, as again with those beacons, the beacons are what's there that the supervisor is sending out just to make sure that there is no fault and the ring is working normally. And then if there is a fault, it'll be detected because of that beacon node that was sent out. After failure detection, ring supervisor unblocks the blocked port. Now that network configuration is now in a linear topology when that happens, and the fault location is readily available via diagnostics. Once the ring is restored, the supervisor hears the beacon, as I said, and then it will transition back into a normal ring, blocking off that port that it uses for emergency purposes. And with that, we are on to PRP, which I believe is David.
That's me. Can everybody hear me okay?
Yep.
Very good.
All right, thanks.
Yeah, sure.
And I think I've got control here. Let's see. Let me try to go forward again.
You just click on that space. Yeah, there you go.
There you go. Okay. All right. Sorry about that. So welcome everyone. Appreciate you taking the time today. And I know a lot of us are multitasking at home. I've got a couple of second graders that I'm homeschooling as well as working full time. So if I do start handing out math worksheets and word ladders, please somebody stop me. It's a confusing time out there. But
Nice.
but before we get into parallel redundancy protocol, we do need to kind of reset ourselves on some of these networked architectures. And parallel redundancy protocol is newer, is relatively new compared to the DLR. So I think I will try to spend a little bit of time with some background on understanding why, its use cases and why it's needed and some examples. So I know we've got a lot of folks out there using DLR today. So focusing on redundant star, as you can see from the three diagrams, yeah, visually it is more complicated. You see more cables. So obviously the ease of configuration is not the same as a ring or a linear. And the more boxes you see means it does have higher implementation costs. So that's why we've got the reds on the diagram for redundant star. However, redundant star has a very important place within the operational technology space. And so what it does give you, as you can see, it gives you additional bandwidth. So looking at the ring, all the bits and bytes are going around the ring one way or the other. Here with the redundant star, we've got multiple paths. And so with multiple paths, you can increase your bandwidth. And the other thing that's really one of the drivers of this in the operational space is the redundancy options. And so you can tell just by looking from the diagram that, yeah, I've got, not only do I have not a single point of failure, I actually can sustain multiple failures in different locations and the network can still communicate. And so that right there is your first key differentiator from the ring, where the ring can take one hit, still operate. The redundant star can take multiple hits. So that would be your first use case example, would be if I've got a network that if I have one failure, now I'm down to no more failures with a ring. If I can, a network that can retain multiple failures might be a good fit for some critical applications. And the other thing here we have, if you notice on the screen, we have redundancy and convergence, and we have readiness for network convergence. And so as someone that's not an inherent network expert, I looked at that and said, okay, why is convergence written twice on my slide? Well, because they mean different things. And so if you look at redundancy and convergence, and Brandon did a good job of explaining the convergence in a ring network. What we mean by that is how fast can the network repair itself? And that's usually in time. And of course, the DLR is very quick. So within 3 milliseconds or so, the DLR ring can come back. Well, a redundant star, because it can retain multiple failures, doesn't have a convergence time after your first failure. So that convergence time would be 0. So that would be another use case example in a redundant star. And if you look at the bottom, the readiness for network convergence, and that means something a little bit different. So in preparing for this presentation, I actually had to Google convergence or network convergence because I wanted to understand the base definition and where it came from. And so when you Google network convergence, because it was originally an IT term, you get a lot of IT type definitions. And so I think the original network convergence was related to combining telephone, video, and data communications into one device and into one network. And so a lot of IT, a lot of our companies and things have done that, and it's allowed us to function quite well during this time, is that network convergence in the IT space. So for our purposes though, we have operational technology and operations customers and products. So how does that relate to operations? Well, I think in a lot of ways, if you think about networks in the past, we had serial networks, we had coaxial networks, we had a lot of networks in operational technology before we had Ethernet. And so today, as Ethernet has become the primary OT technology as well as IT, so how do we prepare ourselves for that Ethernet or that Ethernet IP network convergence? And so with the redundant star, and hopefully you'll see in the next few slides, there's a lot of options available to you as you converge your plant-wide networks to an Ethernet technology. And so that's why we've got those green blocks there on our slide. So with that being said, so the redundant star was an original IT technology. So the next logical step for us is, well, how do we implement redundant star in an OT space, in an operational space? And so so that's where Parallel Redundancy Protocol comes in. And so, or PRP for short. And PRP is a standard. So the IEC group got together and created a standard, and it's listed there, the 62439-3. And one of those offshoots of that standard was PRP, or Parallel Redundancy Protocol. So in keeping with the basic design of the redundant star, you've got a fault-tolerant, fully redundant Ethernet infrastructure with Parallel Redundancy Protocol. So if you see from the diagram here, oops. So we've got LAN A and LAN B, and as you can see from the arrows, the same packet is sent from one controller, and it goes down 2 parallel paths, hence the name Parallel Redundancy Protocol. And then it goes over to your other controllers that need that information. So the same packet is sent through both LANs, meaning there are 2 parallel paths. So if one path is disrupted, the other path, because it's independent and because it's parallel, it continues to communicate. Therefore, with an entire LAN failure, you don't have any convergence time required on a PRP system. So what are good applications for PRP? Well, first of all, where redundant network infrastructure is a requirement. And that, again, that multiple failure option is desirable. So where we see this going in, a lot of process applications, oil and gas, water, wastewater, et cetera. But we also see this as a kind of a backbone of maybe a DCS type network where you really don't want to afford any kind of downtime. ControlNet redundant media was another one of those options that kind of lends itself well to PRP, and we're seeing customers looking at that now at their older ControlNet networks. So with any kind of a standard that comes out, there's a whole lot of terminology. So this screen here is an attempt, I think a pretty good attempt to explain a lot of the terminology involved. with parallel redundancy protocol. And so I'm going to do my best to explain this. And so I'm going to try to do some annotation here and see how well this works. Hopefully you can see my mouse. If you can't, where I'm looking at here are the ControlLogix chassis. So we've got 1 at the top and 3 at the bottom. And what you can see there from each ControlLogix chassis is you have a DAN in the controller chassis and a DAN in the IO chassis. So a DAN or a DAN is in PRP terminology is called a dually attached node. And so what that means is that node is connected directly to both LANs. So your most critical infrastructure, control infrastructure, is going to be on this. It's going to be a DAN or a dually attached node. So you are directly connected. You've got all the benefits of PRP directly into this hardware. And so similarly, so you may have situations, and when you design networks, it becomes certainly something that's common, is you have some existing systems that may not support the new technology, or that may not need, in this case, you may not need that parallel redundancy, but you also want to be able to communicate with it as well. And so there's another device, and this is a panel if you look at the right-hand side, we have a panel view here that's designated an SAN. And so an SAN is a singly attached node. And so what that means is an SAN is attached to one of the 2 LANs. So in this case, the panel view is attached to LAN B. It's not attached to LAN A because the panel view doesn't have the PRP technology built into it. And I think you determined that, well, maybe we don't need it on both LANs. So we can survive if our panel view is just on one of the LANs. So it's not critical infrastructure. Now you have that in between piece. Maybe you have some older technology that needs that redundancy, but there's no way to directly connect it to the PRP network. And so in order to do that, you look at the bottom of the screen here, and we have 2 things. So we have what we call a red box, and that's short for redundancy box. And so the red box has the ability to connect to 1 or more PRP networks. And so this particular 5400 static switch can connect to one PRP network. And so what this red box allows you to do is to connect other devices that don't have PRP inherently in their devices, but you still want that information on LAN A and LAN B. And so these devices here, this is a drive and a Flex IO stick. Those are called VDANs, or a virtually dual attached node. And so you do have that one piece of singularity of a single point of failure here, but once you go through that red box, that information is on both LAN A and LAN B. So that's a quick overview of the terminology. Actually, before I move on, and at the end of the PRP section, I'm going to give you some links to go and learn more information about PRP. And one of the important things when you learn about PRP, you learn about what you can do, but it's almost more importantly what you cannot do. And so one of the big rules about PRP is, because these are parallel paths, LAN A and LAN B, the primary rule is you cannot connect LAN A and LAN B together. They have to remain parallel independent paths. And so we have lots and lots of documentation that explains that, but I just wanted to go over that real quickly before we move on. Okay, so moving on with parallel redundancy protocol. So the next question you may ask is, okay, how do I connect my PRP network to my plant-wide infrastructure? So in the plant-wide infrastructure, so what we've been talking about up to this point is a control network, most likely within one LAN or one virtual network. But how do I bring that up to a layer 3 network or a routable network or my enterprise system? And so the way to do that here is documented on this screen. So what we have here are a set of redundant industrial Ethernet switches, and we recommend the Stratix switches for this. So this this diagram here is showing the Stratix 5410s because they are redundant. They support the HRSP infrastructure here between the two nodes, and so those switches do support connecting to a PRP network. And I won't go into the details of that. Some of the details, the bits and bytes, are explained in some of the manuals, but they are they do support what we call the jumbo frame sizes. And again, I'm not an inherent network expert, so I won't go into that. But we do support the important part of this is we do support the plant-wide connectivity to plant-wide infrastructure. Okay, and some more details. So how do we do this? So how do we build a PRP network? So first of all, what we have to understand is PRP packets are just like any other packet, but the PRP or the DANs in the PRP network, the dually attached nodes, have the ability to send these PRP packets, and so that differentiates. So that's why the ControlLogix and the Flex 5000 pictures you see there, those are two pieces of technology with Rockwell that do support the parallel redundancy protocol, and they can send and receive the PRP packets. So, but the LANs. So how you get communication between the controller and the I/O? Through the switches. We recommend those being Stratix managed switches. So 5700s, the new 5800s, etc. Those will support the LAN topologies in between your DAN networks and your red boxes, etc. So again, so network convergence times, and this is an important thing with redundant networks. There is none with the parallel redundancy protocol. Compared to any other ring network, is going to have some sort of a switchover requirement. And so how does this sort of work? And at a very high level, I'll explain it. So the PRP nodes, or the dually adjust the nodes, will send out two packets simultaneously. And what happens is on the other side, the receptor of those packets will receive the first packet. It will take that data and ignores the second packet. So essentially, what we call this is the first person wins. And so that's why the PRP DANs and the red boxes have that type of communication that happens in the parallel redundancy protocol. But these devices, again, they only have one IP address and they only have one MAC ID. So that keeps it somewhat simple. Now, in the future, and Luis can maybe chime in and help me out, I do believe that in the ControlLogix, we are supporting multiple PRP nodes or in a chassis. I don't know if that's out yet, but I know that's something that's on the near-term horizon for Rockwell.
That's a good lead into the next slide that I'll be.
Okay. All right. Yeah. Great. So anyway, so Luis will talk about that further. So I think I'll move ahead. Okay, so a little bit more about the red box or the redundancy box. So within Rockwell Suite and the Stratix, there's two options. So we have the 5410 and the 5400. Both can act as red boxes inside a PRP network. And so you see some of the attributes there. So and what's interesting, and we're just getting into some of these architectures here. I have a few more slides. So you look at here on the right, you have a PRP network. So you have LAN A, LAN B, to the left of that, you have this red box that's connected to the PRP. And because it's a 5400, it also has 3 rings hanging off of it. So that's one of the benefits of the PRP is you can connect quite a few different type of architectures inside of a PRP. So you can have 3 rings in a Stratix 5400 and be connected to a PRP network. Oops. I think I skipped one. Here we go. Okay, so and then to finally, one of the, again, the ControlLogix redundancy does support PRP as of version 3105, and so this is a quick diagram of a redundant chassis in a PRP network, and I do think we're going to see more of this down the road with our high available applications, because the zero network convergence, I think that it looks really good on a specification, and I think it does. I think in some instances it becomes a good topology. Okay, so a couple of links here. I'm gonna open up, or I'm gonna talk about. The first one is the application technique manual, and this is a really good manual. This gives you a lot of different architectures that are possible with PRP, and it's about a 60-70 page manual, a lot of diagrams. This particular diagram here demonstrates a PRP network with multiple VLANs. So without getting into a whole lot of detail, multiple VLANs is something that is possible to do in our converged plant-wide Ethernet model, which gives us the ability to separate data between devices, but still use the same network infrastructure. And so there's a lot of reasons why you may want to do that. And implementing PRP still gives you the ability to have that functionality of the multiple VLANs. And there's also a white paper, and so this is a short read. This is about a 5-page white paper. It provides a really good overview of solutions of the PRP system, and provides a lot of use cases. So I would recommend, if you wanted to have a few minutes and want to get some little more details about PRP, this would be the first one I would look at. It would be the PRP white paper. And finally, we have the design and implementation guide. And so this is the big manual. This is where a lot of the nuts and bolts come together. So if you're looking to implement or design a PRP network, I would highly recommend looking at this. Not only does this manual provide a lot of examples of capable network architectures, it also tells you what not to do. And so sometimes in building networks, that can be more important. Understanding the limitations and what not to do. Again, like connecting LAN A and LAN B together. And so, as you can see from this diagram here, it is possible in a PRP network to have dual rings. And so this is just one of the many examples of capabilities. And not only does the dual rings have all these ControlLogix, but you also has some drives on it as well, connected via the red box. And finally, one more architecture drawing. This is an example of SIP sync with a time synchronization system using a GPS antenna. So again, this is somewhat of a more complicated type of network that's used, but that has a very strong use case. This can be implemented inside of a PRP network as well. And so there's probably 10, 15 more diagrams like this in all our documentation. So just want to get that out there, and that is my last slide. So I will turn it over.
Sounds good. Let me see if I can request control. Morning, everybody. So my name is Luis. I am with Rockwell Automation here in Houston. As Wayne mentioned, my title changed recently, so I'm now a process solution consultant. So I focus on process and cybersecurity opportunities, still mainly pre-sales, covering a bit more area than I used to in Houston. So pretty much everybody on the call. One of the things that we wanted to kind of review is as we start talking about resilient networks and talking about DLR and PRP, one of the things that we want to also look at is, well, normally you guys have seen we have ControlLogix, so we're able to do ControlLogix redundancy. So what we'd want to do also is look at the ability of being able to do redundant adapters. So if the opportunity calls for a redundant infrastructure where you're looking at redundant controllers, potentially redundant switches, you may also be looking at redundant IO paths. So a couple of things that we're going to go. 1715, for anybody that hasn't seen this before, this is, in short, is our redundant IO. We've had this available since probably early 2014, so it is not a new product by any stretch of the imagination. But it does allow us to do the ability of being able to bring in one sensor into two distinct IO cards, and it's a redundancy per channel. So what we'll see is the first purple ones there are redundant adapters. We have two distinct adapters there. It does support device level ring, like we have talked about. And you can also just do a linear or star topology. So as we start looking at it, you have the ability of being able to do digital in, digital out, analog in, analog out, redundant cards. All of that is tied directly into ControlLogix, so you don't have to do the programming for the voting. And in simple aspects, if you guys want more information, the slide or the IO cards themselves can go up to 24 IO cards. So we have the adapters that are there. And as we bring everything in, typically we see this for your critical systems that require redundant IO, or even a process safety solution that would require up to a SIL2 implementation. We do this with ControlLogix, either a fault tolerant with a redundant controller, or even a fail safe with just a single ControlLogix adapter going to EtherNet through this connection. So fault tolerant IO, this does provide everything in. The IP address, in most cases, what you'll see is you'll have DLR incoming connection there, jumper cable, and incoming going out. So everything is taken care of as part of the system, and this would interact as any other remote IO capability within ControlLogix. So similar to how you would interface with Point IO, ControlLogix IO, we'd have the same look and feel. For something that's a little bit newer, about a year ago, we introduced the 1756 EN4TR. We do have a new firmware that will be added to this to provide some extra capabilities. So when you guys are looking at DLR, typically you're looking at the 1756 EN2TR. David just talked about the PRP, that parallel redundancy. You would look for the EN2TP. And I know all these acronyms and everything is confusing, so please follow along. But what you'll also see is now the EN4TR will be a newer generation Ethernet adapter. It is a gig connection, so it's not limited to 100 megs. It would be a gig. It would have solutions for both PRP and DLR on the same card. And then the firmware that's targeted for the end of this month, hopefully within a week or two, this will be just the firmware that you download from our process compatibility download site, PCDC for short. Once you add this into the system, you're going to be able to do two cards. So it has a redundant adapter similar to what we just saw with 1715, but you would see this especially for your remote IO chassis. So some of the examples that you're seeing here is you have a redundant ControlLogix up top that would still have the EN2T. You can either do a single connection there. You have your redundant connections for the controllers. And then as you approach the remote IO, you have two cards there from an application point of view. DLR generally gets you a resilient network. So you have two Ethernet pairs that are coming out and you can survive a single fault. Typically what an argument that we hear out in the field is that if the card itself were to fail, or if you lose power, let's say to that specific rack, this would then provide you that extra bit of protection now that you have a redundant adapter, so you no longer have a single point of failure at the card level. So we'll see this added in. Some of the, obviously those connection pieces. And then another ability that you would have here is looking at the ControlLogix redundancy. So we could support the PRP infrastructure, similar to what David was talking about. So now with this would be a similar idea with PRP, the parallel redundancy. What you're seeing here is you can have two distinct Stratix switches. So that would be our Stratix 5700 or 5400 connected up to your IO network through the ControlLogix on the top end side. If you needed to have a single switch in between the ControlLogix adapter or processor to the IO, the requirement would be that switch in the middle would need to be a red box. So again, it would be that Stratix 5400 that David was talking about if we're looking at a single switch there. Out the chute, the easiest way to set this up would be in form factor of a DLR architecture, the device level ring. So at this point, we still have redundant ControlLogix up top. We may have a switch so that you can have your tie-in for any other networks, depending on what you're doing there. Some of the slides that we're going to show you in a little bit are some of the newer technologies that we have around device level ring. But now what you'll see is going into the EN2TR, you'll have the two adapters, and similar to how we set up the 1715, we just have a jumper cable in between. So the two connections here, you have one connection going out, one connection going in. One of the big things that you see as a benefit with device level ring is the ability of being able to see the diagnostics from IP address to IP address, but you will be able to see this as we tie in. Again, this is just kind of going in. You can simplify this. So if the requirement is just that you have a redundant adapter, but you don't necessarily need device level ring or potentially even PRP, you do have the ability of just supporting this with a single ControlLogix chassis. This can be a small little 4-slot L7, L8 with your communication card, and then that going down to the EN4TR. The main issue, as you guys are all aware, is this becomes a single point of failure. So in normal recommendations, we probably would have put this here. But if you do have a requirement, you may potentially have redundant power supplies, redundant adapters, redundant media, redundant switches, redundant controller, and then potentially even redundant software on the top end side. I like joking how much redundancy is too much redundancy. Depending on the needs, depending on what the requirements are, that's where we would put together a listing of everything that you guys are seeing. Everything is usually based off requirements, use cases, but just know that all of this exists. So if we start needing this, as David mentioned, one of the things that we're probably going to start seeing more and more along the process space, or even with PlantPX, we now support both device level ring and PRP, that parallel redundancy. It really just depends on how we're doing the architecture. Just a little bit more information on this. The 1756 EN4TR, one of the other reasons why this became a big hit for us last year when we introduced it, it does also support SIP security. So we introduced that in a previous user group. I think we have it slated for a month from now or so to go into a little deeper dive on this. If we're looking at the EN4TR at the controller level, we'd be able to support the SIP security. In terms of introducing this into the larger redundant adapter, right now the SIP security is a future release for the redundant adapter portion of it. But if we just have a simplex EN4TR, SIP security, the policy manager, all of that would be part of it. And one requirement that we typically tell you that at this point, it doesn't matter. When it comes to the redundant adapters, we would require slot 0 and slot 1 to be the ownership of those redundant adapters. Usually we tell you the Ethernet adapters, the RM2 modules can go wherever you want. In this case, they do need to be in slot 0 and slot 1. And I think there was a quick update. Somebody was asking about looking at the L8 redundancy. So we, like it was mentioned in the chat, we will have more information on that. We are slated to look at PlatPX 4.5 and the release of 33. So we are slated to see L8 redundancy support at the end of the summer timeframe. But with everybody, we'll make sure that you guys have all the information. And as we continue with the webinars and Zoom meetings, we'll provide you more information as we go forward. Just to touch base, this is, you guys have already seen this, so I'm not going to go into it with a lot of detail. Some of the other things that we want to look at when we're looking at the topology options is not necessarily from an IO or the controller side of it. You may want to be looking at just the switch architecture. So some of the things that we're going to be talking about, or I'll just update you guys on, is, oh, I'm going the wrong direction. Oh, okay, there we go. So I lost my title, but what this is Ether channel. So one of the things that we look at from a switch level design for the resilient Ethernet, so not necessarily looking at DLR or PRP, but just the ability of being able to tie in your access switches to, let's say, the distribution switch layer. At that level, that may still be a Stratix switch at both ends. It may be a Cisco Catalyst switch at the top end on something that you might have for your server cabinet. We do have a couple of options of being able to do your loop prevention and making sure that you have a dual path. In most cases, again, you're trying to remove your single point of failure. So as we start seeing this, one of the technologies comes from a Cisco-based technology that is adopted inside of our Stratix switches. And this would be across the board with all of the switches, including the 5800 that will be coming out soon. This would be called Ether channel. A short way of saying this is link aggregation. The idea here is you would have two connections from one switch to another. You would create the connection and configuration on both switches, on the top and the bottom. And what ends up happening here is it's not a primary secondary system. It's essentially forwarding the information from both ports. So as you start sending the information from one switch to another, you're aggregating the link. So if it's a 100 meg network and you connect two, your bandwidth now goes up to a 200 meg. If you have a gig connection on both, you have a 2 gig. You are not limited to 2 connections. You can actually go multiple connections on here, and that link aggregation just continues to add as you add more connections between the different switches. If you lose a connection, the big plus here is there's no, we talked about the convergence time. So that reconvergence time, when we're looking at Ether channel, there's no reconvergence time because both of them are forwarding. All you end up doing is you drop down to your single bandwidth aggregation. So if it was a 2 gig link, you lose one connection, you go down to a 1 gig and everything kind of reassesses itself. So this is something that's already inherent in the switches. Typically, this would be more of an IT-based design, but we can take advantage of it in an OT world. It doesn't have to be from access to distribution. This could be from just panel to panel, but something that we would configure. All of our Stratix switches have what's called spanning tree protocol built in. By default, they are configured as MSTP, so it's multi-spanning tree. What this allows you to do is it's loop prevention. One of the big pluses that we see in a managed switch environment is the ability of being able to tie in 2 connections and making sure that we're preventing a loop that knocks down the rest of our network. So as we start looking at this is your base connection. So you would have a forwarding and a blocking port. Similar idea to what we would do in the device level ring or and tie-in. So this is a loop-free side of it. Our biggest thing that we would tie in here is because of the fact that you are forwarding and blocking, losing the forwarding and having to open up the blocking port does require more reconvergence time. So this isn't necessarily something that we recommend as a default, even though it's a default for the switch. This is something we traditionally change over or recommend maybe using device level ring. But just know this is the default setting for your static switches if you don't do any other configuration. One other ability being able to tie in multiple switches, and again, this is a Cisco-based technology that we adopt within the static switches, is rep. So you might hear this occasionally when doing more of a traditional ring. This is a resilient Ethernet protocol. So as we start seeing this, we do have the ability of being able to tie in multiple switches either via fiber or copper. You can do 100 meg or 1 gig. The recommendation on this is not to mix speeds. So when they're in networking in general, you're usually looking at your weakest link being your issue throughout the entire thing. So if you have a 1 gig chain all throughout, and then you have a 100 meg connection in between, you're essentially at 100 meg all the way around. So you do want to make sure that you can mix media type, but you don't want to mix speeds. So typically what we'll see here is rep is one of the easiest methods of being able to tie in multiple switches in a ring. But again, you'd be looking at reconvergence time. So how long it takes the switch to reconfigure and your connection from one point to another. That could be anywhere from 50 milliseconds to about 250 milliseconds, depending on a number of different variables that go on inside of the switch. So what we typically recommend, both Rockwell, TRC, if you guys provide us any documentation regarding your networks, is we're probably first going to be looking at a device level ring topology, which you'll see in a couple of slides we can do at the switch level as well, or potentially a redundant star topology similar to the Ether channel, potentially even flex links, or the PRP design that David was talking about. So I'll let them continue, but I'll be here if you guys have any other questions. Feel free to chat it in, or I'll chime in as we go through. Thanks, guys.
All right, thanks, Luis. Let me just take the control back. All right, so we're going to close out here with just some architectures and kind of going back to the device level ring, where we kind of started the discussion earlier. So most customers and end users of device level rings probably have only used it as it truly is, as the name implies, right? Device level, from like controller to controller or controller to remote IO drop and back, and perhaps not even realizing or knowing that you can intermix industrial switches in those rings. So over the past couple of years, Rockwell has released kind of, they've called them phases 1, 2, and 3 up to this point. And going back a couple years to 2018, they did what was called phase 1, where it was basically that architecture we just saw a minute ago with the rep ring, but as a device level ring of switches. And then last year, phase 2 came out, where there was a mixed, kind of a mixed ring, where you had switches and devices themselves in the ring. And then here in just the last month, phase 3 was tested and validated and released, and that is now bringing in redundant gateway into the ring. So we'll kind of look at the architectures here real quick. And again, all of these slides will be available after. So I know there's a lot of architecture drawings that we've thrown out there along the way, so they'll be referenced. Also, I should note the link at the bottom of this slide is where all this stuff comes from. There is a deploying a DLR within a CPWE design guide, and they go into exhaustive detail of how these rings are architected and some of the testing that went around it. So when we say tested and validated, what we mean by that is Rockwell has actually built this ring, and they tested it, and they threw a lot of traffic into the ring through some simulation hardware that they have, and they were able to kind of validate and say that if you build it in this way, you will get the convergence times that we've been saying all along. So 3 milliseconds has been kind of that standard DLR convergence time out there. So everything that they've kind of tested with has been kind of standard, you know, Rockwell hardware. So from a switch standpoint, these little blue boxes all throughout the ring are typically 5700s or 5400 Stratix switches, which are the ones that support DLR protocol. All of the devices in the ring itself are, you know, L8 controllers or even a redundant L7 ControlLogix systems. They have some GuardLogix in there, as well as drives and remote I/O devices like Point I/O as well. And everything as of the latest phase 3 has been tested with the latest firmware. So up to 32 firmware in the controllers for ControlLogix controllers. So the first one, this is looking back to phase 1. So so just a switch level ring. So the tested limit here was up to 24 switches in this ring. And again, a single speed only here, right? So either a 100 megabit ring or a 1 gigabit ring, and with a single VLAN. So this is fairly interesting architecture because you can bring in a lot of devices into this. We've always, again, the published limit has typically been 50 devices in a device level ring. With a switch level ring, we can tie off a lot of other equipment into the ring through the switches. So all the way up through perhaps a full, Class C subnet, 250 such devices, into this ring. And phase 2 brought in the mixed again, so some switches and some devices themselves just directly into the ring. So in this case, we're back to the 50 ring node kind of limit, and once again, we were through the testing that was done here, convergence time was 3 milliseconds based on this, and this was again. Will be one ring speed, of course, throughout this one. And then the previous one was actually at 100 megabit, I should have said. So this next one was basically doing the same architecture, but at a 1 gigabit speed. So with that, we would have 5400 switches, as well as the newer L8 and 5069 I/O in this ring to support the 1 gigabit speed. And again, 3 millisecond convergence time was validated. Now here's an interesting one. David had mentioned it earlier too, and this is a capability that hasn't really been maybe known that well, is that the 5400 switch can support 3 separate rings off of that one switch. So the 5700 switch, of course, can only do 1 ring. The 5400 switch can do 3 rings, 3 independent rings. So in this example, each ring is the same speed, 100 megabit. And you can see they're kind of a combination of the types as well. So one ring is nothing but devices. The red ring is a mix of switches and devices as well. So definitely increasing the capability. And again, as we see our applications on the plant floor become more and more complex, we start to see things like this. These kind of architectures become more and more commonplace. So the other thing you do with the 5400 multi-ring is you can actually have now mixed ring speeds. So one of those rings could be 1 gigabit ring, and the other one could be a 100 megabit ring. Of course, you still can't have mixed on the same ring, but you could have 3 rings and each running at a different speed. Now into phase 3. So now they basically went back and tested these same architectures we just showed, and now with redundant gateway capability. So kind of bringing in some of the resiliency protocols that we're talking about a few minutes ago. They've tested out redundant gateway up to that distribution layer perhaps. Typically what they tested here were using flex links and ether channel as those resiliency protocols to be the uplinks out of the ring. So again, looking through that design guide, they do give some guidance as to perhaps what is the best resiliency protocol to use for the uplink in these various situations. So this first one was just taking that first switch level ring and with a redundant gateway in it. And their recommendation was either flex links or ether channel would be appropriate for the uplink. Second test was the mixed ring, so 100 megabit mixed ring with switches and devices with the redundant, with the redundant gateway, and again, flex links and ether channel wound up being the recommended solutions for that resiliency protocol on the uplink. And then looking at redundant gateway in the multi-ring situations. So this first example is a redundant gateway with 3 rings, mixed ring speeds, but a single VLAN throughout. In this case, FlexLinks is the preferred resiliency protocol up. And in the last example is multi-VLAN, so kind of that same one, multi rings, mixed speeds, each ring being on its own VLAN. And in this case, ether channel was the recommended resiliency protocol. All right, so just to close it out, we've talked about a few different references throughout. So there's a lot of links and a lot of documentation. It all kind of resides at Rockwell's website, just kind of knowing where it all exists. But there's a lot of white papers and design implementation guides, or DIGs as they're kind of referred to, all around the CPWE. There's a separate DIG just on DLR. There's a separate paper on PRP, and so and there's a whole resiliency dig as well. So that goes in through all the resiliency protocols. So we're gonna again, all these links, lots of them, lots of documentation out there. So just want to at least let you know that it exists, and you can explore these links later. And we don't want to go down the IAB discussion, but if you are integrated architecture builder savvy, then you can build up all these kind of architectures we've been showing inside of IAB. That's probably a whole nother topic for another session to show how to do that. And with that, we have reached the end of the presentation.